Yeah. Thank you very much. Ladies and gentlemen, let me first express my gratitude and my pleasure to be here. I spent a wonderful week already at this institute, and I got a lot of inspiration by that. My talk will try to focus on parabolic geometries from the point of view of constructions of new geometries out of given geometries, which are of very algebraic nature and which are not that easily found if you don't know the background. And the very first one, construction of that kind, was done by Charlie Fefferman quite long ago, when he constructed a circle bundle over each generic hypersurface in Cn, which carries a natural conformal structure, and the conformal structure, of course, being constructed naturally from the CR structure, that is of big help in studying the initial CR structure. So the aim here will be talk about similar constructions. We've got not only wonderful week here, but also during the weekend I got a lot of inspiration on a nice hike in the Bukhan Sun Mountain. So it looked a bit wet there, but very beautiful, you can see. And so I will dare to come to some more or less new example in the very last 3 slides. So on the right-hand side, which is definitely due to our nice walk. Cartan connections are or can be viewed as a curved deformation of the Maurer-Cartan form on the Lie group G, whereas the homogeneous space G over G mod P just is equipped with the trivialization of the tangent space by the left invariant vector field. It's a matter of choice. We could also have chosen right ones, but we should skip to the left invariant vector fields. And you also have the structure of the principal fiber bundle G over G mod P. It can be relaxed a little bit so that it makes sense for every principal fiber bundle with the structure group P, which is a subgroup in a given Lie group G. You don't see the G at the principal fiber bundle. The G doesn't exist there, but you have the principal action by the subgroup P. You've got the fundamental vector fields coming from that actions, and you still require that the one form omega, which is a absolute parallelism, so a linear isomorphism if restricted to each of the tangent spaces and valued again in the Lie algebra G. And the fundamental vector fields have to be respected as they were, because they are analogs of the left invariant vector fields on the Lie group. And we also require the equivariance with respect to the principal action, which is the most we can, because that's what survives from the Lie group. By the right multiplication, you keep the left invariant vector fields invariant, and that's what's happening here. So whenever we get to the situation where we deal with a principal fiber bundle over a manifold with the right structure group P, then we can make many categorical constructions. And the categorical constructions allow us to get the associated bundles, which are strict analogs or extensions of what's known from the homogeneous spaces and representation theory as homogeneous vector bundles. So whenever you fix a vector space V with a given P representation, we get not only the nice homogeneous vector bundle on the homogeneous space G mod P, but we also get the associated vector bundle. So I'm always distinguishing this G is the Lie group, and the curly G is the principal fiber bundle with the same structure group P as we have chosen here. That's not great. So what you get there is really a strict analogy to the homogeneous case, except it's only fiber-wise. Fiber-wise, they look exactly the same, as well as the principal fiber bundle looks exactly the same as in the homogeneous space. But the way how you identify your individual tangent spaces with the tangent spaces at the element at the Lie group, which is the role of the one form omega, just changes fiber by fiber. So in particular, there are much nicer modules than the general ones, and these are those where the P representation comes as a restriction from a G representation. The reason is that whenever we have a G representation in the background, we can use the canonical extension of the principal fiber bundle G to a bigger principal fiber bundle, now already with the structure group G. We just use the P as a subgroup, and we get this principal fiber bundle. And because the one form omega is living on the curly G, which is clearly a subspace here in a canonical way. So if we just use E, the unit, as the element here in the fiber, in the coordinate, then it gives you clearly an embedding of the curly G in the curly G with tilde. And so you can just define your new form omega tilde as being equal to omega on tangent vectors which are tangent to the G itself, and you extend it by the equivariancy which is required for principal connections. And it's a simple check that it's done the only way, and it always exists. So you equip G tilde automatically with a principal connection, and therefore you get the induced connections on all the associated bundles. That's again a categorical construction which works everywhere in differential geometry. And therefore, whenever you get one of these nice vector bundles, you end up with a vector bundle with a genuine linear connection which is natural to the geometry. So the problem of all the Cartan geometries in general is that unlike the homogeneous model G over G mod P is reductive, where everything splits algebraically, and you can also split the Masaryk-Cartan form into a principal connection form part and a soldering form part. Everything is messed up, and the nice linear connections exist only on bigger bundles than, for example, a tangent bundle. On the contrary, in most situations, you can never get a natural linear connection on a tangent bundle. But in particular, for example, if you take the adjoint representation, so the Lie algebra G itself, as a representation of the group G, then you get what we call the tractor bundle, the adjoint tractor bundles. And another good choice is if you take the standard representation for the Lie group in question. And then what you get, standard representation in the case where the Lie group in question is one of the nice matrix groups. So then you have always this regular representation which comes from the representation of GLN, where n is the rank of the matrix which is used for the elements of the group G. So this is very important, and it comes back to the early beginnings of last century, where Cartan worked out a procedure how to get such geometries, and in parallel then people like Veblen or Thomas in particular, would just construct the parallel transport directly on these strange standard tractor bundles. But there is a very general, very wide class of geometries which behave very similarly each to the other, and we call them parabolic geometries because they come from special choices. The special choices are, we take semi-simple Lie groups G for the Lie group in question, and a parabolic subgroup for the subgroup in the homogeneous model. And as for the general category of Cartan geometries or Cartan connections, the morphisms are morphisms of the principal fiber bundles which intertwine the Cartan connections via their pullbacks. And in the case of the parabolic geometries, the point is that we almost get nice algebraic structure. That's the main feature. And the nice algebraic structure is always a grading which comes from G minus K and ends up with GK. And here inside is a part which is just consisting of all the negative elements in the grading. Then we have the G0 here, and here we have all the positive elements in the grading. And this bit is the parabolic subalgebra P, and actually what I have here is the Levy decomposition. And the Cartan-Killing form always makes these two things dual to each other. So that's the general structure of a semi-simple Lie algebra whenever you choose a parabolic subalgebra. And a parabolic subalgebra, for those who know the structure theory but are not familiar with the parabolic ones, the parabolic subalgebras are just those which contain some Borel subalgebra. And up to conjugation, they are all of that form. And that's the way how Cartan and later on many more people came to this type of geometries. The point is that the geometry on the manifold is mimicking very firmly the grading at the Lie algebra level, but only in the sense of P-invariant objects. And if you look at the adjoint action of the group P, so it's always shifting the elements in the grading to the right-hand side. And so the graded components are not invariant themselves. What is invariant is the filtration, which is also the right filtration, which is defined by the grading. So the P-invariant things always start with some GI, and you have to add everything to the right. And that's exactly what's appearing in the manifolds if you start with a Pfaffian system of ODEs. So you get some distribution, which is the analog of G minus 1, and then in the generic case the distribution would be bracket generating the whole tangent space, and so you consecutively build the filtration by taking more and more brackets, allowing more and more brackets, and you have the associated graded bundle. And if the filtration provides you with a filtered manifold, it means if the filtration is compatible with the vector field brackets, then you can ask whether the Lie bracket coming algebraically from the Lie algebra is the same one as the Lie bracket provided by the vector fields. And if this is the case, we say that the infinitesimal structure which we get from the filtration at the manifold is regular, and that's the basic for the construction which Cartan did in many cases, and then later on Tanaka and his school extended that and made it into a beautiful theory, just solving the equivalence problem for all the lot of examples in one move. And still later on, Tohru Morimoto and Keizo Yamaguchi and further people around just extended it to many more examples where it's no more in the realm of parabolic geometries. So the next point is the normalization in the procedure, because the way how Cartan just already did his construction of the geometry was that he started with the Pfaffian system and some symmetries or automorphisms which were working only in homogeneity 0, and then he was increasing the group and building the principal fiber bundle without calling it like that. And on the way, he normalized the things in order to get curvature of the system as small as possible. Because unlike in the homogeneous case, where the Masaryk-Cartan form says that, so the Masaryk-Cartan equations say that d omega plus 1/2 of the bracket of omega is 0, in the curved world, just the fact that it changes fiber by fiber results in having a curvature here. But using the absolute parallelism omega itself, we can define a curvature function which is defined in such way that we just apply it. So these are elements in G minus, so the negative part of G, and we apply it to omega minus 1x, omega minus 1y, where omega minus 1, omega inverse stays for the constant vector field. So it's just the real analogs of the left invariant vector fields given by the absolute parallelism. And the curvature function has clearly values in cochains of the Lie algebra cohomology. And the principal feature of the parabolic geometries is that in the Lie algebra cochains, you've got this algebraic Hodge theory, because you get a joint codifferential, and this provides you with a uniform and a nice natural normalization. And therefore, the cohomology then determines the structure of parabolic geometries, and the original Cartan and Cartan-Tanaka theory can be rephrased in the way that you say that the category of the infinitesimal structures I tried to describe at the level of the manifold is equivalent to the category of the principal bundles with the Cartan connections as I defined them, which is a very strong object, whereas you start with some weak structure. The next striking feature is that not only the harmonic part of the curvature, because the cohomology just governs the normalization, but it also tells via Bianchi identity that the whole curvature of the geometry in question vanishes if and only if the projection to the harmonic part vanishes, because I just did not tell that the Rice normalization condition is that the codifferential of kappa is identically 0. And therefore, if you have this normalization, you may project the curvature to the cohomology. And the striking feature is that using the so-called Bernstein-Gelfand calculus, you can reverse it. I will not mention what the Bernstein-Gelfand calculus is. It's just for those who know already. It's depicted there. But the theorem is that there is an explicit differential operator which, hitting the harmonic part of the curvature, gives you the whole curvature, and it's just sort of uniformly computed. Nowadays we can do it via the so-called curved Casimir operators. It's a curved generalization of the Casimir operators from the representation theory. And the VGG calculus was introduced by Andreas Čap, Vladimir Souček, and myself some 10 years ago. Somehow very lowered better. So let me now focus more closely on the Fefferman constructions themselves. So I just needed the scene for the parabolic geometries to make clear what I'm after. But now we can come back to very simple algebraic structures. So the goal is to compare two different homogeneous spaces by means of some neat construction. So let's have two real or complex parabolic homogeneous spaces. So in both cases, G and G tilde will be semi-simple E groups, and P tilde will be parabolic subgroups. And we need some assumptions. We get a fixed homomorphism, which is infinitesimally injective. We get the requirement that the G orbit of the origin in the second homogeneous space is open, which is the same requirement as supposing that the induced map from G to G tilde mod P tilde must be surjective. Next, we need that the original parabolic subgroup contains the pre-image of the P tilde, so the P tilde must not be too big. And if we have these three conditions satisfied, then we can construct a nice thing, and that is we get the natural projection of the homogeneous space G mod Q, because Q is definitely a closed subgroup of G, usually not parabolic, over the original homogeneous space G mod P. And the homomorphism induces a smooth map which covers the G orbit of the origin in the second space. And therefore, because the image is an open subset, so we can pull back the geometry, so the Cartan geometry of type G tilde P tilde, which is one of the parabolic geometries, back to obtain such a geometry on G mod Q. So in the special case where the embedding was SU P plus 1 Q plus 1 into SO 2P plus 2 2Q plus 2. This is the original Fefferman's construction, and you can see the embedding very nicely in a matrix form if we choose the right metric to define. So Hermitian form to define this SU, it will have this blockwise form 1 and 1, 1 and 1. And the G minus part is here, so it's a contact parabolic geometry which corresponds to the hypersurface CR. And we embed it into SO just by the obvious embedding. And here we get the same structure where here is something which is computed by the other columns in the G minus, and there remains one more dimension in the center because it's slightly bigger, and it's a purely imaginary part of the center, which is C in that case, and therefore just integrating it back down to the homogeneous space, it becomes a circle bundle. So you see, that was the original construction by Fefferman. Yes.
These first three properties don't use hyperbolicity of G or
no.
P, right? It's
no.
just the last one.
Yes.
So, okay.
I mean, it's just what you need. So we don't even need parabolicity. It's just it's just homogeneous spaces. So whenever you have this, you can do what's below. So especially it may happen that actually the inverse image of P tilde is the group P. So then in the special case we get Q is P, and that's very special, because in that case both parabolic geometries live on the same space. So basically you get an inclusion of one parabolic geometry into another parabolic geometry on the same manifold. This is equivalent to the condition that the action of G on the G tilde mod P tilde via the homomorphism I is transitive, and the stationary subgroup of this action coincides with IP. So this comes to the, so this leads us, so this observation leads us to the inclusion problem. Actually, now I'm coming to a common work with Boris Dobrov some years ago. And this was our original motivation to start this problem. So there were two quite recent examples. In that time, these were very recent examples. And it's the non-degenerate rank 2 vector distribution of 5-dimensional manifolds, which were studied by Pavel Nurovsky, and some elder considerations, but written up very recently by Robert Bryan concerning 3 distributions in 6-dimensional manifolds. So let me just very briefly sketch the two examples. Pavel Nurovsky just reconsidered the original Cartan's most famous construction of the 5 variable papers, where you deal with rank 2 distributions on 5-dimensional manifolds which are as non-degenerate as possible. So they have the quickest possible growth. 2, 3, 5. That's what you can get. Yeah, very good. That's what you can get. And Elie Cartan has already proved that there is a natural G2 geometry associated with any such distribution. So basically it's amazing that this was probably the first construction coming to G2 ever, such a complicated one. And Pavel Nurovsky noticed that this geometry can be extended into conformal geometry of signature 3-2, and thus there are the natural cones of null vectors under Tm associated with any such 2 distribution. The second example due to Bryant takes the rank 3 vector distributions, and the non-degeneracy says that the brackets generate a whole lot of Tm. And Robert showed that there is again a natural conformal geometry associated with each such distribution, and he used the spinor representation to show that there is a genuine conformal cone again of split signature geometry on the manifold M. So both examples have striking similarities. So I don't mean that everything what I mentioned up to now always ends up with some conformal geometry. That's not the rule. But they both start with non-degenerate vector distributions and generate out of that some other parabolic geometry. And the associated parabolic geometry can be embedded into much nicer parabolic geometry, much simpler parabolic geometry, the conformal one. And so there was the natural question, what are all possible embeddings of one parabolic geometry into another? And the other question was, what was the geometric meaning they had? And it's very good to have bright collaborators who know all the literature, because once we notice that it's enough to look at the homogeneous spaces, and if there were such embeddings, then they must exist also for the complexifications. And Boris just knew by heart that there are some works on that from '61, and it was just a matter of very quick search, and he found out the list. So if G is simple and complex, then Onischik just classified all the cases where the group of biholomorphisms of the homogeneous space, keeping the structure fixed, is bigger than the original group itself, which is just rephrasing the same question in a much more general way. And this is all the examples which are there. So you see case 1, case 2, case 3. So I will not go through the letters here. I will rather tell what it is in the realm of real parabolic geometries. In order to see what these complex geometries allow for real filtrations and gradings, you just have to run a very simple check on Satake diagrams. For those who know Satake diagrams but don't know the result, it's easy. You get the parabolics by crossing out some of the knots, getting the shape of the upper triangular block upper triangular matrices, and simply the crosses tell you where the edges in the blocks are. And the rule is if you cross some white knot, which is linked by arrow to another one, you have to cross the other one as well, and you must not cross any black knot. That's it. So that's the classification. So if you go through this check, you see that actually there are very little real forms, already only the split forms. And so you have 3 series of examples. The first one is the very well-known projective contact structures and their relation to the projective structures via the Fefferman-like construction. So it's a very nice construction, basically, actually, and not that elementary, because the projective contact structure means that you have a contact structure equipped with projective class of partial connections on the on the contact distribution. So you differentiate only in the contact directions. And the associated projective structures are obtained by taking the chains of the contact projective geometry in the complementary directions to the contact distribution and the well-defined non-parameterized geodesics inside of the contact directions. And these curves together provide you with the curves which define the projective structure. It's very nice to see. It's obvious you can expect it, but it's difficult to prove. The second case is just the Cartan's G2 geometry, giving us the Nurovsky's example. And the third series of example boils down to the Bryan's case in the very lowest dimensional case, L equals 3. So all these constructions are very special instances of the Fefferman construction, where the base manifold do not grow, and as we have seen for simple groups, there are no more. Let us now devote our attention to the third series, and there is a paper on that which we wrote together with Boris Dobrov and will appear very soon in a special issue of this Pure and Applied Mathematics Quarterly in honor of J.J. Kohn this year, I guess, or next year, I don't know. But we already had the Galley proofs, so it should appear pretty soon. So let me tell some more details about the free distributions now. So that's the third line of examples where we've seen only the lowest dimensional one due to Bryan. So the reason why Bryan restricted himself only for dimension L equals 3 is that actually the choice of the conformal geometry as the new bigger geometry is not the best one. It just works only in dimension 3. What you have to do is you have to consider the free rank L vector distributions on a manifold, which means that the codimension of your distribution is exactly as big as the space of the antisymmetric matrices of the same size. That's very good choice, because you see that satisfying the condition which are very briefly told on the infinitesimal structure to be able to provide the construction of the parabolic geometry over that, it means that the algebraic bracket obtained from the vector fields coincides with the bracket at the D algebra level up to isomorphism. So you can just equip the tangent space, so the filtered tangent space, with the appropriate structure, is here a generic condition, because up to isomorphism you've got just one possibility to write down a non-degenerate bilinear 2 form on n-dimensional vector space, which is vector valued with that big dimension. So that's the easy way. So you see also immediately that the structure will be 2-graded, because it's just a similar structure, block structure like here, except the blocks I have at the matrix will have different dimensions. And so without doing a single step, just having the Cartan-Tanaka theory, and in particular the way as we have it with Andreas Chapp and others, linked to the cohomologies and very simple or quite simple construction, we just know in advance that there will be a unique normal Cartan connection of type G mod P, which is associated to these free rank L distributions. But not only that, just computing the cohomology, you compute easily via the Costan's version of Bott-Borel-Wales, so just using some software for that, that the only harmonic part of the curvature will be this particular bit of torsion. So it's some similar thing like in conformal geometry. You know that the curvature starts at homogeneity 2 level there, and then the Weyl curvature is the only invariant to kill all the curvature. And here the only invariant is just already in homogeneity 1, and it's this part, so trace-free part of this torsion. So it eats one argument from the distribution and one argument complementary to the distribution. So of course in the lowest dimensional case it's different. There is the Weyl curvature or some analogy to that. So thus the essential part of the curvature is obtained already in the first prolongation step. So that tells you that knowing it in advance and knowing how the normalization is from the general theory provides you with tools for very, very simple computations or relatively very simple computation compared to what the people have done in the literature. And you compute explicitly out of the, you start with any basis of your distribution, and then after doing some 3 steps of computations in one page, you just compute explicitly your p's, and you know that's the only invariant. What about the Fefferman construction now? So it's quite clear how it should look like if you view it at the level of the Satake diagrams or Dinkin diagrams. We are working with the split form, so they are the same. So we start with this. So this is the parabolic for the free distribution, and we simply embedded it into one dot bigger one. We'll just separate sort of the double link and keep the cross on over one of those. So this is the way how it works. And you see that basically if you want to get this embedding, you have to have the image of this guy inside of the isotropic subspace for the external automorphism, just swapping these two things. So it wasn't such a difficult task to guess the embedding, and the explicit form is in front of you. And so what we end with on the right hand side is what's called one-graded spinorial geometry. So it's called spinorial because you put the cross over the fundamental spin representation. So one of the fundamental representations of the SO case. So again, the embedding goes from odd dimensional B case into even dimensional D case. And the DL+1 geometry, which we seek for, is the so-called spinorial geometry. So there, for the spinorial geometry, the geometry looks like the negative part of the corresponding Lie algebra. And again, just looking at the spinorial thing, if you cross the very last node in the diagram, in the notation, then the G-1 is here, and you may choose the metric which defines your split geometry and SO in such a way that the matrix will be antisymmetric but along the anti-diagonal, which means that there will be zeros all over this line, and it will be antisymmetric this way. So let's see whether it works. Yes. So now the question is how to construct the new geometry out of the old one. And it's quite straightforward to see it, because there is the tractor bundle, the standard tractor bundle for the initial one. So the initial geometry was this one. So this was again antisymmetric this way, so it's 0 here. And here is the G-1, so it's the L-dimensional thing, so it's L1. So here is something you just compute by the antisymmetry. And here you have the G-2 part. And if you put the standard representation here, just this R2L+1, then already in the first prolongation, you get the splitting of this bit into the two slots. And so that's coming from the filtration, which is on the board there. And as a G0 module, the standard representation splits this nicely to RL plus R plus RL. And so we get a G0 module S, which is just isomorphic to RL plus 1. And you see, because the adjoint representation is just the skew symmetric tensor power of this one, the whole lot. So this lower bit provides S isomorphic to lambda 2, no, the other way around, lambda 2S isomorphic to Tm, which is just what we wanted, because that's the way how the spinorial geometry is defined. So you see, we consider just S as a vector bundle, it's well defined, and then we get the natural isomorphism. And this is exactly the required spinorial structure. Yes. So, what about the Bryant's example? So why is the Bryant example the same thing in the lowest dimension? Well, it's because the triality of D4. So it doesn't matter where you put the cross if you have just 4 knots. But it's a very bad argument for those who are not very familiar with that. You can also see it in a very, very explicit way, because identifying the tension space with skew symmetric matrices, you've got the cone of the degenerate ones. And this is given by a determinant, but in our dimensions, because it's just for odd L's. So for odd L's, you get the Pfaffian, which is the square root of the determinant. So for the L equals 3 case, you get 4 by 4 matrices, and the Pfaffian will be just quadratic form. And so you get the product as you wished. Well, there is now the next problem related to these geometries, because almost you automatically, by the very construction, starting with the first parabolic geometry and doing the Fefferman construction, you automatically arrive at a new connection which is naturally constructed from the old one. But you don't know, in general, whether the connection constructed this way will again satisfy the normality conditions on the curvature. That's an open question in general. So for example, in the original Fefferman's case, so the construction itself works not only for hypersurfaces in Cn, but you can take also the almost integrable CR manifolds, or codimension 1, which are obtained automatically on hypersurfaces in almost complex manifolds. But there, if the geometry is not integrable, then aside of this regular curvature from the CR case, where you have just one curvature in homogeneity 2, so except dimension 3 where it's different, there is another torsion, and the torsion just is responsible for the integrability. So it's just the Ninus tensor of the complex structure on the contact distribution. And if this torsion is non-zero, then the new connection built in the construction for the conformal case will not be the normal one. It will be another connection. So the conformal structure is well defined. So basically you've got two Cartan connections there, one which comes naturally from below, and the other one which is the normalized one. And no one has yet studied the difference between them, how to use them. Everyone was happy to know that it's working if and only if it was integrable, and then it's just automatically giving a normal connection. So here we wanted to solve the very same problem with Boris, and we asked under which conditions the extension of the BL geometry to DL+1 geometry would be normal. And we were afraid and told by experts like Andy Chubb that definitely it will be if and only if the torsion vanishes, and then it's not interesting because it's locally the homogeneous case. But fortunately it's not true, because you see the theorem is that it vanishes identically if and only if one particular bit of the curvature vanishes. And because, as I told you, so we haven't computed it yet, but in principle, using the curved Casimirs, you can explicitly compute the operator which gives you the full curvature out of the torsion, which is the harmonic part, and so you would get just the explicit description then in terms of differential operator on this very particular invariant, and this one vanishes, it's the K11 part, then it's true. But of course, even knowing that, it might have happened that there are no such examples. So fortunately, there are other people working along, and Stuart Armstrong had, for some other reason, already an example, which is very simple and shows. So that's the homogeneous space. And if you deform it very little, then you get a very strange sort of Cartan space with nearly constant curvature, which just, because all the curvature there is just concentrated in the harmonic part only, and in particular the K11 is 0. So you see we've got an explicit example of a geometry where the prolongation would be normal, so I mean the Fefferman construction would provide directly a normal connection, and still it's not flat. So let me finish in my last 2 minutes very quickly, just briefly mentioning an unfinished project with Gerd Schmalz.
Can you say in the previous example why it's not flat?
Because there is a non-zero curvature. You can just compute the curvature explicitly, and the curvature is not zero. So it's an ongoing, very old project, which for some strange reason we didn't finish with Gerd Schmalz. So if you replace the orthogonal algebras by special unitary ones and go along whatever I was telling here about these particular examples, you get a very nice example of high codimensional CR geometry. So it's codimension n square, so real n square, because this G-2 block on the lower left corner is formed by skew Hermitian matrices. So instead of antisymmetric, they will be skew Hermitian. And the size of that is n square. The corresponding parabolic geometry is induced on generic surfaces on real codimension n square in a little bit bigger Cn plus n square. And if you compute the cohomologies, so in the first cohomology, the only component is of homogeneity -1, thus the entire geometry has to be determined by the filtration only. And if you go further, then there are two components of the second cohomology. One of homogeneity 0, which would just give you something like two different brackets already at the infinitesimal flex structure. And the other one is of homogeneity 1, so it's a torsion, quite similar to the free distributions. If you go on, you can also use very same embedding. If you remember the matrices some slides back, so you would just replace the transpose to star, and it's just working. So it's basically working in the SU case, and you just put together the two crosses, because the right picture for the embedding in the language of the diagrams is you take just this guy, and you embed it into one lot longer one, but only with one cross in the middle. So in the lowest dimension is just this guy. So the new SUN plus 1 and plus 1 geometry is the only one-graded geometry for the SU case. And it's very similar to the spinorial one. So you define it by identifying the tangent space with a space of skew Hermitian morphisms on some auxiliary complex vector bundle of rank n, n plus 1 here because we are n plus 1. And in the lowest dimension n equals 1 we recover the hypersurface type CR structures and the original Fefferman construction, because you can notice that the determinant on skew Hermitian matrices of rank 2 provides a quadratic form on the Lorentzian signature, and it's given up to rescalings only because the structure group G0 is the whole lot of GLN plus 1C, so it's just up to constants. And that was actually the last slide, yes. So you see that you can just recover the whole situation for this exceptional, very, very high codimensional CR structures for the sort of Hermitian-free distributions in very high dimensional complex spaces. So thank you very much for your attention.